Hello and good morning to the fourth AAIC of this year, the Applied AI in Semiconductors and Silicon. We are hosting this event now for the first time together with Silicon Alps. So I also welcome Mr. Hartwin Kostron on the stage with me. Hi, Hartwin.
Hello, welcome.
And Matthias Grabner from the Austrian Economic Chamber. Hi, Matthias. Hello. Can you hear us, Matthias?
Now I can hear you. Hello and good morning.
Excellent. Perfect. So, yeah, we want to, before we start with the keynote program of today, which will be kicked off by Infineon later, we want to give you a brief overview. First of all, what is the AAIC, who are the organizers, and last but not least, some basic housekeeping of how to handle the Q&A and so on. Yeah, but before we start with the self-intros, I would like to hand over the word to Hartwin to give a brief overview of Silicon Alps, because you're a first-time partner for the Applied AI conference. And yeah, please tell us a little bit what your organization is doing.
Thank you, Clemens, for the introduction. In a short notice, I am responsible for marketing and development of the PR agenda of the Silicon Alps and also the Silicon Alps region. So Silicon Alps is a network organization in the south of Austria, and we are more or less a high-tech cluster. We have a network of more than 125 plus companies and research institutions, and with the goal of fostering cooperation and innovation in and outside our network for the sake of society, of course. So at the end of the day, everything we are doing is for society and bring together the interests of the public and of the industry and of research institutions. So we have been founded in 2016. We are public-private network connecting the electronic-based systems ecosystem, and we are in the hand of 11 shareholders. The core topics involve everything revolving around electronic components and systems. And this is also, I think, one of the most important touch points of AI and what the Silicon Alps institutions and companies are doing, because the goal of everything we're doing is, of course, becoming more efficient, saving resources, and reaching the goals of the Green Deal and everything that makes the world a happier and more ecological place. So basically, I think artificial intelligence touches almost all of our core topics that we deal with in our network, which is smart production, of course, predictive maintenance, cybersecurity issues, so everything that makes the internet, but also systems a more secure place or a safer place to be. Systems integration, of course, embedded systems, and so on. So we have many applications of AI. And I think it's needless to say, and it's no secret, that the application of artificial intelligence or AI solutions along the value chain will become a key differentiating factor for businesses in the next decade. So I think it's a very important topic that we work together here. It's, of course, the key to efficiency. It further decreases ecological footprint, as I said before. And of course, this is very important for the semiconductor industry. And the semiconductor industry is, of course, the heart and the heartbeat of the Silicon Alps cluster, because we involve some of the major chip supplying companies to Europe and also to the world. So this is very important. We will hear about that later from the people themselves representing their organizations. And I think what is important to all of us is fostering cooperation and collaboration, fostering the bonds. And this is why public institutions such as Advantage Austria is key. Initiatives and societies such as iAustria is also very important to advance clusters as more or less a neutral position on the site, and also giving input to all of our organizations. And then we have the big topic of European sovereignty. So I think big markers and landmarks that came across in the recent weeks and months, such as the IPCI 2 approval by the European Commission, with more than 150 million euros funded for 3 of our key players in microelectronic business, is a good prospect for the future, I'd say. So I think that's a good starting point to advance all of our agendas and getting more sovereignty in a global perspective. But I think here is also to mention that we need, and it is important to work together on a global scale, because competition at the end of the day is not a question of wealth. It's a question of equal chances for the nations, their regions, and their people. And such a region is Silicon Alps region, of course, in the south of Austria. And this is one of our goals to, of course, bring the agendas further and be one of the representatives institutions that bring them together, also in the view of Silicon Europe Alliance on a European scale, where we work together with Silicon Saxony, which we will hear later on the day in the program. So I think this is a very important step to work together, and therefore I'm looking forward to the conference today. And at this point, many thanks to Clemens for the organization, and yeah, looking forward to the content and the keynotes we're gonna hear afterwards. So thanks for that.
Thank you very much for the great intro, Hartwin. Yeah, as far as the event is concerned, or let's say maybe a couple of words about AI Austria. This is the non-profit, which you can see behind me here. AI Austria is a non-profit organization which has been formed in 2017. Our launch was actually at the very first Applied AI conference, because this is something we initiated together with the Economic Chamber. The work we are doing is, on the one hand side, create awareness for AI. With this is not so much going in the direction of, let's say, the techies, like most of the audiences today, but rather to talk in a broader societal context. What are the implications of AI? That it's not that the killer robots will be at our doorstep tomorrow, but rather what to expect in terms of automation, which ethical questions arise. We also run a couple of training programs, so either for people that want to switch careers and or for high school students. For high school students, we did this together with the Ministry for Education. Here it goes mostly in the direction of what happens with your data, what is machine learning, why is it data-driven, what can it do, what can it not do. More interesting, I think, for the audience today is we are also collaborating very closely on an international level. So, for example, we are very active in the European AI Forum. I will post the link later in the banners. The European AI Forum takes place once every 6 months and is hosted by the Bundesverband KI. This is like the German pendant to AI Austria, Hub France, IA, and many other AI organizations. And here we really have a very open exchange with high-level officials from the European Commission. So, for example, we always have a combination of ministers and EU commissioners, where we talk about, on the one hand side, about AI regulation as such, and on the other side about broader topics, especially like the ones that Hartwin just mentioned in his initial statement. Good. As far as housekeeping is concerned, I now move Matthias on the stage. Hello, Matthias.
Hello, thank you, Clemens.
I see you switched devices for the 3rd time, but 3 times is the charm.
Yeah, it's very hot in Vienna for all of those who are not joining us from Vienna, and especially in my office where there's no air conditioning, unlike in Clemens' office. The computer crashed because it's too hot. So as far as it comes to housekeeping, today we are only streaming over LinkedIn and also on our YouTube channel, but most of you are joining us on our LinkedIn stream. This is all live. We have no pre-recorded sessions, which means that you should take the possibility to join the discussion, and you can do that by interacting with us in the stream, in the chat section of the stream. When you post your questions or your comments in there, we will display them, we will react to them, as long as they are not simple marketing messages for your company or your services, please understand. But if you want to contribute, yes, just like this, our friend Jan Bruckner from the US Commercial Service, we will get you in the discussion, and feel free to ask our speakers and us anything at any time. Good morning, Werner. Hello. Well, Clemens, I missed part of the introduction, but my question to you is, can you share a little bit on why we are doing this on semiconductors?
First of all, because it's super interesting. That's always the most important thing to do an event where you also expect people to watch. I think it started around 3 years ago when Springer Professional was reaching out to us to do a deep dive on why is there this reignited interest suddenly in specific chips and architectures for artificial intelligence. This was also around the time that the first Google TPUs, tensor processing units, became available in the cloud, and so on and so on. Initially it looked like this is the typical hyper capital intensive topic where you expect China and the United States doing 99% of the groundwork. But it turned out that especially in Europe, both UK and continental Europe, you have lots of startups emerging and also lots of research activity going on. This is like coming from the chip design or custom design corner. And of course, you have a very large semiconductor industry in Europe since ages. So it just made sense to dig a little bit deeper to showcase what's going on in Europe, which directions are the companies pursuing, and how is it organized. With how is it organized, I mean, if you look at China, I think in the last 12 months, more than 6,000 semiconductor companies were formed. So this is mostly venture capital driven. In the United States, it's always a combination of DARPA and venture capital, but what is the European approach and so on? So this is also one of the topics we would like to dive into. And yeah, with regard to the time, we explained already everything. I think since your computer, I don't want to melt your computer, so we could directly start with the first keynote.
No, you're melting my phone.
That's okay. They don't melt so easy. So with us for our first keynote today, it's my special pleasure to welcome Infineon Technologies, the team from Germany. So with us is Mr. Dr. Thomas Altenmüller. Hello, Mr. Altenmüller.
Hi.
Dr. Yao Yang.
Welcome.
Good morning.
Hello. Good morning.
And
Good morning,
Ms. Natalie Gentner. Good
Hello.
morning.
Good morning.
So yeah, I mean, obviously,
we're really excited to have one of the.
Exactly, that's what I wanted to say. Yeah, no, we are very happy that you joined us. We are even more happy that it was in one of our last events actually that me and Mr. Altenmüller got in touch via LinkedIn, and this is how basically this speech came into place. I will not spoil too much what you will present, because this is after all your stage. Me and Matthias will leave the stage now. We put the slides here, and once you're finished with the presentation, we will come to the stage again and handle the Q&A session with the three of you together. So without further ado, the stage is yours, and see you later.
Okay, thank you very much, Clemens. So then let's have a start. You can hear me well enough, right? Looks like. Okay, So we are talking about applied AI at Infineon. We want to present some of the novel AI approaches and solutions in Infineon production. So my name is Thomas Altmüller. I'm dealing with manufacturing analytics at Infineon here in Munich. And with me is Yao and Natalie, who are core pillars to our data science team at Infineon. And we will talk about Infineon and the production topics that are supported by AI. So therefore, we will first start a little bit with Infineon and AI. So give you maybe an idea to remind you what Infineon is. After all, we are one of these age-old semiconductor players in Europe, dating back to actually 1848, because you don't have to forget that we are a spin-off of Siemens. Since 1999, we are totally independent. No more Siemens, but in that sense, our roots trace back 150 plus years. So very proud Europeans, which means that we are so global that Yao actually enjoys to join us here. We will talk about defect classification, which is vital, obviously, for semiconductors, about predictive maintenance, and also anomaly detection and version metrology, and also about the challenges that specifically the WIP flow in semiconductor manufacturing, front-end manufacturing poses, and address how we address these topics with all the nice toys of applied AI. So basically, maybe first some words about Infineon. Infineon is, as you hopefully know, a leading player in the semiconductor industry. We are actually the number 10 worldwide. We are globally positioned. We have a network of front ends and back ends. Front ends manufacture the silicon wafers and the circuitry, and back ends then assemble it into these typical black beetles that all of you know. And we are actually everywhere in America. We are in Asia Pac. We are obviously in Europe as well. We have factories in the US, in Mexico, in Indonesia, in Malaysia, in Singapore, in China, and Korea, and of course in Germany and Austria. We are a leading player in automotive and in power management and drives, in sensor systems and in connected secure systems. And we are largely geared towards automotive, as you see from this nice pie chart here. But we are also very present in everything that is related to industrial control and power management in general. And also what was formerly the ship card business is now more concerned about connected security. So basically, if you think about Infineon nowadays, what we think ourselves of is this circle of sense, compute, actuate. So like perceive, think, do. Yeah? So basically, we all know these PDCA cycles. This is now the semiconductor version, sense, compute, actuate. And unless or different from companies like Intel that focus like on compute, we do actually the full circle. We do compute with microcontrollers and specialized memories. We do actuate with our highly acclaimed, I would say, power semiconductors that can handle super high voltages, like several thousand of volts, and very high currents to drive industrial equipment and even like high-speed trains. And we sense the environment by our nice portfolio of sensors, including like power pressure, pressure sensor, magnetic sensors, optical sensors, and all that kind of stuff. This enables us actually to connect to the real world, be it cars, smartphones, computers, drives, industrial IoT, you name it. And that connection then actually, we can actually use to connect the real world to the digital world. And that is one of our new mottos, if you like, that Infineon links the real and digital world. And I think here, specifically now in this age of IoT, we can add a lot of value. We add this value in different ways. One part of the value, of course, is actually supporting our customers with new digitalized products and services. Another part is, of course, supporting our own production and manufacturing and value chain by digitalization and integration of the value chain. And all that together then leads to this new business models and customer experience that hopefully will bring us forward in the next decade. Here, of course, in this meeting, we will focus on the digitalization within manufacturing. This is what we as a team focus on, and this is actually what we will present today. That means actually digitalization within manufacturing means generation and analysis of data from manufacturing that you can use to gain knowledge, make predictions, and automate decision-making. I mean, you have to see that actually the total flow of manufacturing in the semiconductor industry, as you probably all know, actually is a very long way, going from design and development, buying the right raw materials like silicon wafers, manufacturing that into integrated circuits on round wafers like this in our front ends, then assembling it in the back ends to this black beetles, and ultimately basically bringing it to the customer so that we can support the success of our customers by our solutions. We here now will focus largely on front end. Front end is actually a completely fascinating area. Just to remind you, in case you don't know and not are from our semiconductor area, this great area, it is actually the most complex thing that humans ever created. If you look at a manufacturing site producing semiconductor wafers. So it runs 24/7 the entire year. Actually, it connects all kinds of different tools like furnaces, implanters, etching tools, metrology, lithography tools in a very, very intriguing pattern that actually will lead to 1,200 process steps per wafer that are layer by layer basically deposited on these wafers. We use up to 1,000 tools in a clean room, which are all connected. And that leads to a WIP in our factory, wafers in progress, of around 100,000 lots active at any moment. And these lots, these wafers, usually stay for a very long period, 30 to 60 plus days in one factory. This here on the right side is actually the layout of our factory in Regensburg. And just to give you an idea, these are all huge halls. You see here the scale in meters. So it's roughly 200 by 200 meters. And one lot is traveling through these halls over 40 kilometers in total. And it will actually change buildings 130 times. Means actually that lots in these type of factories, they see 15,000 transport moves per day. And each lot will travel 800 meters alone. You see, this is super complex. And all this needs to be handled by very sophisticated systems. And here, obviously, comes AI to our support. So AI supports our factory manufacturing with speed and efficiency. Examples are analysis and prediction of the WIP flow, automated decision-making to the extent to dispatch what lot, when, and where to. But it's not only about factory manufacturing, it's also about equipment stability and control, which gives us higher productivity. This is about detection and understanding and predicting events. This is something that Yao will elaborate on. And it's also about yield equipment correlation, understand all the data flow that comes from the sensors in our tools to make the most sense of it. This is actually what Natalie will later focus on. So actually you see that AI can support semiconductor operation and Infineon, that is, in many, many aspects. And to give you maybe just a short list of the things that we will cover here, we talk about predictive analytics, like predictive maintenance, anomaly detection, or process optimization, virtual metrology. And we will touch here on use cases like the ion source lifetime in implanters, the health factor of equipments, cycle time prediction through the factory, or to analyze the ordering behavior of customers. For image analytics, which is one of the most dominant topics in AI, of course, image classification has a huge benefit for us as well, because we can actually do defect classification using deep learning. We can recognize anomalies in these detections. There's this kind of fun thing mousetrap dust calculation. And the technology behind that is CNNs and the usual well-proven exception VGG16 nets and all that kind of stuff that you probably know from all the AI talks that you attended to. And of course, natural language processing is as well very important because it will help actually maintainers, for example, to classify the root causes based on the past experience, which is actually documented in natural language. So this is just the methods that we use. These are the use cases, and these are the application areas. And with that, having set the stage, I will hand over to Yao, and Yao will tell us something about defect classification and predictive maintenance. Yao, please.
Yeah, thanks, Thomas, for your introduction. Yes, the first use case is about defect classification, and that falls in the second category Thomas just mentioned. So in our front end and back end manufacturing, we have many different image classification tasks. For instance, the defect in the density inspection, the outgoing inspection, and some other special topics. However, currently, most of them are done by hand, that is to say manually, or not at all. So if you do such kind of inspection manually, it is slow, it is expensive, and it does not scale at all, and it's also prone to human error. So our goal here is actually to increase the operator, to develop AI solutions, machine learning solutions to increase operator productivity and to get value out of the unused or underused data. Next slide.
There it is.
Yes. Here we make use of transfer learning. That to say, we start with VGG16, we move to exception, and finally we end up with efficient net. And here we use a two-step approach. That to say, first we only train the top layers on new data, and then we fine-tune the weight on all layers. For use case of like first of a kind, that to say, a brand new use case, we first do transfer learning. That is to say, we use ImageNet weights directly. And after that, after we gain some experiences, we have some trained models, and we then transfer learn from most similar use cases. So by doing so, we can have faster learning and by better final accuracy. Currently, we're using the native TensorFlow implementation of EfficientNet. For a batch of 23 images, with our GPU, our training time is about 550 millisecond. Sorry. And what's very important here is we revisited the labeling of more than 20K images. That to say, we invite our domain expert to revisit to check whether the labels of this more than 20K images are correct. After that, we see that the model performance is largely increased. That is to say, here we show that data quality actually is more important than algorithms. Only after we have checked the data quality, we improve the data quality, our performance is increased. Yes. And the current flow is like, okay, if we have input images, we put the image into our model. If the model can classify it as of one of our focus class, we leave it like that. And if the model classify the input image as not focus classes, or the model is not very confident about the classification of the image, we leave this yellow and red cases to manual review. Regarding implementation, basically our model is implemented in a Docker container, and we have a business application in between to connect our existing manufacturing system, like job controller, to our Docker container. Yeah, so that's how the model is implemented. Yes. That's the first use case, image classification. The second, we talk about predictive maintenance. That falls in the first category of our overview picture. That is a predictive analytics. So here we talk about iron implanter. So if you can see here, our wafers goes one by one through our implanters. Sometimes we see unexpected repair, unexpected schedule downs. Since our implanters are very expensive, such kind of unexpected repair can be very costly. So in order to forecast that, we do some historical data analysis. We do data collection, data cleaning, and we extract features. And here we really talk about big data, because we need months or even years of data. And then we feed the pre-processed data into our models. Here we consider different variation of the modeling approaches. We considered a simple feed-forward neural networks. We considered LSTM, the long short-term memory. We considered 1D CNNs, and in the end, we also used temporal convolutional networks. So in the end, the model can provide us predictions on a daily or hourly basis. So in this way, we move from reactive to proactive, which means that we can better plan our repair.
Right.
So currently, as I said, we have automatic daily prediction, and we can achieve precision of 90% and recall of 60%. That is to say, if we predict, let's say, failure in the next 24 hours, 90% of the time we will see such kind of a failure in the next 24 hours. And the 60% recall means, okay, if in total we have like 10 failures, we are able to identify 6 out of it. Since this is a very promising result, we decide to scale our method to other work centers and also other sites of Infineon. Based on our experience, actually scaling to other work centers or sites is not a direct copy and paste. So direct transfer learning is not possible, because different work centers, they have different set of available input features, and sometimes the same neural network architecture is not possible either, because the work centers, they have different behavior. Therefore, our neural network architecture has to adapt to the behavior of the target work center. However, we can use the same problem-solving steps like I listed here, from step 1, data collection, step 2, cleaning, step 3, feature engineering, step 4, modeling, and finally, prediction. With each iteration, our learning curve is getting steeper and steeper. In the end, I'll show you the, here first on the left, I show you the how our prediction looks like. So here, the blue dots in the figure shows the predicted time to failure, and the magenta line shows the real time to failure. And in order to make it easier for our maintenance engineer to understand, we translate the blue dots, the predicted time to failure, into probabilities. So like shown in the middle picture, so with the help of the dashboard, our maintenance engineer can adjust their maintenance plan according to the prediction. With this help, they can increase the source life hours, and they can reduce the source maintenance, which in the end leads to increased uptime and also cost savings. That's about the 2 use cases. Next, I would hand over to my colleague Natalie about anomaly detection and autoencoders.
Thank you very much, Yao. The work represented, or the next 2 applications I'm presenting, are based on a cooperative work from Infineon together with University of Padua. As we already seen, the diffusion of Industry 4.0 led to the creation and collection of huge manufacturing data sets. Such large and also heterogeneous data sets represents a challenge when aiming for developing data-driven approaches like predictive maintenance we saw before, or anomaly detection, which I will present now. The anomaly detection we see here is able to handle heterogeneous data coming from different equipment, work centers, or production sites. And the proposed approach exploits deep learning architectures called autoencoders, as you can see on the right side of the slide. An autoencoder is a special type of a multi-layer neural network that performs hierarchical and nonlinear dimensionality reduction in order to reconstruct the input as closely as possible. So the autoencoder goal is to minimize the mean squared error, or a metric, between the input data and the reconstructed data. In order to detect anomalies or outliers, the model first have to learn the so-called normal behavior. And as seen, for example, in the CRISP cycle, the data pre-processing is a main part of that, and a main part of a successful model training. So therefore, the following pre-processing steps were applied here. We removed constant features, of course, because they don't contain important information. We have quite a lot of different recipes running on the same equipment, so the recipe effect needs to be removed. Then remove of redundant information, meaning highly correlated features. Of course, removal of noisy features. And then, of course, we want to scale the whole process. And to give you an idea about the size of an example data set used for such a model training in our case, you see here after the pre-processing, we have around 200,000 rows or samples and over 100 useful features. Okay, let's have a few more details about the training approach and how we manage scalability for such a large and heterogeneous data sets. The development of the architecture, like for example, the number of layers, is automized or semi-automized. It is based on a design of experiment where a tournament search is used, and the tournament search compares a lot of different architectures with their different losses, and the winner is then chosen at the end, so best result. Here, for example, we select an architecture with a bottleneck size of 32. So we have basically a dimension reduction of over 75% with 3 layers each in the encoder and the decoder part. On the left side, we see 4 examples or 4 sensors that are used as input and recreated as output. And now, in order to make use of such a trained model that is able to reproduce the normal behavior, we define an anomaly score and an anomaly threshold. The goal here is we will want to find a metric in order to classify whether a considered data point is an anomaly or not. The anomaly score is chosen in the following way. The anomaly score for each data point is given by, we choose the mean squared error between the original value and the reconstructed value. The threshold then is an upper control limit based on statistical process control techniques. And a data point with the mean squared error above the upper control limit is then considered as anomalous. Okay, the next use case is virtual metrology. So what exactly do we mean when we talk about virtual metrology? The big figure on the slide shows a typical scheme for a virtual metrology technology. Virtual metrology estimations are typically monitored alongside real metrology measures to widen the monitoring perspective. Virtual metrology is formalized as a regression task where sensor data collected from an equipment during a process is treated as input, while this corresponding, for example, inline measurement on the layer or on the product is used as output. So in detail, virtual metrology aims at estimating metrology quantities that are costly to be measured by means of data-driven algorithms. So we exploit the availability of historical data where such measures are performed. Okay, here we go deeper into an example of a standard operation that happens in semiconductor manufacturing, plasma etching. Sorry, it's the other slide. Can you go back? Yeah. So Exactly. So the etching process erodes, as you probably know, a material from a surface or transfer a structure built up during the lithography step on the layer below. Before a substep can start, the chamber has to be in a stable condition. Hence, we have settling times, for example, that has to be taken into account. And often, endpoint detection is used to stop the process whenever it is finished. Examples of the corresponding variables, meaning raw physical sensor measurements, are shown on the right side of the current slide. The signals of two different equipments are marked in blue, respective red. So on the top picture, we see a clear vertical shift between even two chambers or two equipments. In the middle, we cannot visually detect a big difference, but on the bottom, we see a clear difference in the second half of the process. That is actually an issue when we think about scalability of such a virtual metrology prediction. So what we propose is a common virtual metrology model for two identical in design equipments who process data follow different distributions, as we see on the picture. Okay, now we can exactly. So now let us have a look on how the done-based alignment model is set up and what advantages it brings. First of all, we have to make clear domain adaptation is not equipment matching. Domain adaptation is a purely data-driven approach. And the goal is to learn from a source data distribution, a well-performing model on a different but related target data distribution. So let us have a look at the architecture we are using in detail. So first we have data set 1, where we trained already a successful regression or prediction model. Then a data set 2 comes into place, but the data set 2 we recognize follows a different distribution. So we see a difference. And when we apply the data set 2 to the already trained predictor, we fail and see a lower accuracy, which is not satisfying. That is why we introduce a so-called aligner. That means we map the distribution of the dataset 2 to the distribution space of dataset 1. So we have an aligned dataset 2. This aligned dataset 2 can then be used as input for a predictor, and we achieve similar good results as we did for the dataset 1. In this whole domain adaptation neural network setting, a so-called discriminator as a third part is used in an iterative training approach to make sure that the whole process is generalizable not only on the seen or training data set, but also on unseen data. Okay, the advantages are data spaces can have different dimensions. The aligned features are comparable and interpretable. And we can also, thanks to this discriminator and this iterative approach, we can also make use of non-labeled data for this training of the whole alignment.
Okay. Yeah.
Okay. Right. So as already said, the aligned features are comparably and interpretable. So therefore, the role of each part can be nicely visualized. On the left, we see true versus predicted values for two equipments called A and B, before on the top and after on the bottom of the alignment. And we see a clear improvement. The diagonal, of course, is the goal. The accuracy of the reference chamber B is constant because we are not retraining the predictor, while the prediction accuracy for the chamber A or the equipment A is heavily improved. In the middle, we see 6 examples of raw sensor signals before and after the alignment. Blue is the reference chamber B, black the original signal from chamber A, and red shows the aligned signal. As we can see, it is highly improved and the alignment works pretty well. Also for different use cases where we have only a part alignment is necessary, a whole alignment is necessary, or non-alignment at all is necessary. On the right, we see a so-called t-SNE plot, pretty famous or pretty often used in the whole domain adaptation scene. So we see a t-SNE plot of the input data before. You can clearly see the distinction between the two data sets. And after, we see the successful alignment. The two domains or data distributions are aligned. Okay, that's all from my side. For both the applications, there are papers available. So if you want to know more detail, let me know. Other than that, I give the word back to Thomas.
So thank you, Yao and Natalie. The last topic that I just briefly, for sake of time, want to touch is the WIP flow management and reinforcement learning, which is another deep learning approach. Basically, reinforcement learning, you probably might have heard of. It is used in famous applications like AlphaGo. It works like a toddler would work. So basically, you try out action and you look for the consequence, whether you get a reward or not, and what is the state after this action. And from that, you optimize by iteratively running through this, you optimize your strategy. And that is, of course, all possible to do it in a mathematical way. There's a lot of literature about that. And what actually was a breakthrough in the last 10, maybe 15 years was to use deep neural networks for that task. Basically, we use here, in the context of WIP flow and resource dispatching, we use actually an environment which is actually a sandbox, which is actually a simulation of our production chain. Maybe only a partial chain, maybe a total chain, whatever you want to study and where you want to improve the performance. So basically, you will try out an action, which is like picking a certain lot to be dispatched on the next tool, and see how that actually does in terms of a target function, like cycle time reduction, which gives you a reward. And after this action, you observe the state of the system, you observe the accumulated reward that you got, and from that, the agent, the neural network, is forming a strategy that is improving cycle time. And this is actually a quite nice approach that is based purely on standard software, open source. You have your TensorFlow, you have OpenAI Gym, you have a SymPy open source simulation, and we run it on our own Infineon Jupyter Hub, which is our own compute farm. And the nice thing about reinforcement learning is that you basically you optimize your ordering behavior, but actually you do it in a training, and after that you have a neural network that actually can make these decisions ad hoc. You don't have to have each time a full optimization run, which is actually potentially a very, very long compute time. You train it once, and then you can reuse it and maybe retrain it if needed, but basically is able to make ad hoc decisions. And that actually leads to a reduction of cycle time of orders, for example. And this is actually our last example here, the cycle time improvement by reinforcement learning. We use an episodic cycle time reward here. We basically had a 40 machine, 5 worker center setup, so which is already a medium-sized line. It's not a full front-end wafer fab, but it's a partial line that we have sometimes in the back end of line in our front ends. And the reinforcement learning agent was able to develop a dispatching strategy that was optimizing cycle time throughout the total production line. Basically, it did that by trying out approaches, brought in this learning process the cycle time, which you find here on the y-axis, down, and learned to avoid invalid actions. So basically that all actions that it takes are valid and they are good to reduce the cycle time. And that actually, despite the fact, which is actually a major complexity for classical optimization things, despite the fact that this is actually a totally frequently stochastically interrupted machine line, and it also has this re-entrant WIP flow characteristics, which lead to very, very nice nonlinear effect in your WIP flow. But the agent was able to handle it. Here in this example, the agent was actually optimizing the maintenance headcount scheduling in order to have the optimized cycle time. So basically, you can actually make these actions applicable to headcount scheduling decisions, as you can make it applicable to lot scheduling in front of machines. So all these examples of Infineon might be a little bit technical, but they show where we are currently. I want to close with a more programmatic slide. We feel that AI will enable us to innovate faster. And as we already saw, our claim is that our semiconductors are the link between the real and the digital world. And specifically for our own production processes and all kinds of business processes, we already use several AI applications, many actually, that help us to develop, manufacture, and supply innovative products and solutions. And we feel that this is AI is another key element in this continuous journey towards operational excellence and time to market, and all that, of course, for the success of our customers. So that is actually the operative side. And of course, on the other hand, you remember that first slide, there's also a very nice portfolio of AI-supported products, so that our solutions will really enable new levels of human-machine interaction. We will make it trustworthy, power efficient, so that it can be used on the edge AI in a very safe and secure environment, and they will be easy to use and deploy. And therefore, our closing statement is that we feel that all this helps us to make IoT, this industry of things, really work, and that ultimately we do for you, because this will make the life of us all easier, safer, and greener. And that was my closing sentence. Thank you very much for your attention, and we are open for questions now.
Yeah, thank you very much for the very broad spectrum you have shown what is going on at Infineon. We also received a couple of questions, so it's safe to say you didn't go too much into detail, because these questions are also quite specific. So it sounds like the perfect match with the audience. So let me start with the first one. That one is directly addressed to Dr. Yang. Can you see it, or should I read it?
Yes, I see that.
Okay.
What do you think about reinforcement learning, deep reinforcement application for manufacturing? Yeah, for manufacturing, Thomas has just provided a nice example. But for predictive maintenance, I have to admit we haven't tried that yet. But I think it's also a very promising future direction we can follow.
Perfect. When it comes to predictive maintenance, there is actually one topic that is a little bit closer to the base from Mr. Leidinger.
Do you distinguish between prescriptive and predictive maintenance? Yes. Okay. For the iron implanter, actually, we don't, because that's somehow special. We are predicting the source lifetime. And in reality, it is no matter what is the root cause, why, what is the failure mode, the only action is just to change the source. So you don't need to specify how you're going to do after the failure. But that's my understanding. The difference between prescriptive and predictive is, okay, prescriptive might be a little bit further compared to predictive, that you say you have to not only to specify to predict when it will fail, but you have to give your recommendations how you're gonna deal with this failure. But as I said, for iron source, our only decision is, okay, change the source. But for different work centers, that might be might be more useful if we can provide the solution together.
Great. Then one question, I think that is addressed at all three of you, because it covers everything. It's, do you also use a digital twin of your production facilities, machines, processes? I would even extend, or do you use simulation environments in other places?
Yeah, maybe I can take that. So we do. I mean, a digital twin is much more than just data warehouses to store your data. It is also including a simulation. You saw that actually we use in reinforcement simulation, but we have huge simulation tools which are running long-term and short-term simulations of our production sites, our front-end sites. Of course, we also use a lot of simulation in our production, in our development for our devices. So there's an entire wealth of simulation models in our process development. Yes, so in that sense, and we use it also on a work center level, so that actually we simulate in in painstakingly detail the performance of work centers to understand how to improve their behavior and their bottleneck behavior, for example.
Good. Then with regard to reinforcement learning, we have 4 questions, but giving the time, I tried to put them together. So I think the first one here is, did you use vanilla DQN to get your nice results?
Well, we started out.
Yes and no question.
No. It's actually never yes and no. It's not a digital world, actually. Oh, it is. But basically, of course, we use DQN. We started with the DQN, but currently we prefer the TRPO, which is a different algorithm. Yeah.
Great. Then, what's the performance of your simulated environment in terms of steps, for instance?
Yeah, that depends, of course. We run actually some million steps, and it takes us several hours. So we need millions of steps, and this takes on our compute farm several hours.
Good. And out of this block, would it be possible to achieve better sample complexity via model-based RL in the use case you've presented? I could imagine that you might have some dynamic model available for the process.
Better sample complexity. Actually, I don't understand the question, so I say maybe. So
that's always a good answer.
Yeah, so I wouldn't exclude it. Yeah, sounds worth to think about.
Great. Then we have some more questions. Matthias, can
yeah, exactly. And Remco is asking, how exactly does Infineon make it easier for developers to use your microcontrollers in AI-powered products?
Okay.
Do you have a strategy for that?
Yeah, we have a strategy. This is, of course, the different side of Infineon. This is now the product development. Our microcontrollers are used since quite some time and very, very well known for automotive. So we have actually a real-time microcontroller with our Aurix products, which actually is very important if you talk about cars and safety in cars, because it reacts in real time. And also we use more industrial-based XMC and other products in microcontrollers that we got from Cypress, with whom we merged last year. And all this as well is supported by AI algorithms. There's a very nice AI ML library, which is currently under development and which will support developers of AI products with an Infineon-powered AI library for our microcontrollers. Check it out on the internet.
Thanks a lot. Yeah, also Remco sent us a side note. May the best team win today, Netherlands versus Austria. So looking forward to that. Thank you, Remco. Clemens, what should that t-shirt actually be? But let's discuss that later.
Wrong color.
It's salmon colored. I got the detailed information by my wife on that one. It's not orange.
But let's dive back in. Also, Roman sent us a question. Maybe I can quickly put that up. Which transformations does the aligner process without changing moments?
Natalie.
And he sent a follow-up question, maybe to clarify. Did reinforcement?
No, that is probably
that's a different one. Yeah.
Different one.
Who wants to answer? Can
Natalie.
you answer?
Yeah,
Answer the first question.
I can start. So I guess it goes a little bit into the details about which moments, which loss you are actually using for training. And for training the aligner, the so-called Wasserstallmetrik is applied, which goes into expectation values, which makes use basically of expectation values and make sure that you really align the distributions and not just, let's say, maybe a simpler mean absolute error where you really don't have the assurance that you not only make it work on your training data but also on the testing data. So it goes in the direction of which loss you're using, and let's say there we use also a lot of the findings about generative adversarial nets, which is a used topic, especially in the image detection area, where a lot of research is done in the which loss best to use, which metric applied to make it as general as possible, and let's say stay true to the moments or the distribution of your data. So I guess it's all about the loss there and tricks learned from already existing, let's say, related methods.
Mm-hmm. Thanks a lot. Roman, hope that answers your questions. And
So this
Clemens.
maybe the second question, because very super brief. I mean,
Yes.
what I presented on the reinforcement learning was on VIP flow optimization. What this ask here, I understand, is failure rate is more like product development, and that of course is a fair question. You can improve product development as well by having as a reward function something that is quality related. What we do, for example, as well, another domain in Infineon is looking at optimization layout with reinforcement learning. We have some very clever guys there. Lorenzo Sabadei, maybe he can actually give you much more information on that as well.
Mm-hmm. Maybe you can get in touch directly. And thanks for your answer and that clarification. Well, we are at the end of this interesting session, Clemens. But this will not be the last we hear from Infineon, because we have another colleague of you on our panel discussion in the afternoon. And he is active in digitalization and data science in manufacturing, Mr. Staatsacher, on applied AI in semiconductors. Clemens.
Maybe one final comment / offer from my side. Ms. Gentner, you mentioned that you also published 2 papers on that topic, and this actually goes to the 3 of you. If there is any information you want to share regarding what you've just shown, like links to the papers and so on, just drop us a brief email, and we will make sure it's disseminated throughout the conference today.
Okay.
Exactly.
Great.
Great.
Thank you.
Yeah, and with that, really, thanks a lot for joining, also for showing up in comparable large numbers, because normally, even if the company is gigantic, you get 1 speaker maximum. So I think this is highly appreciated, also that you cover a broad range.
Yeah. You're welcome.
And yeah, thanks a lot. And yeah, we're looking forward to see you at one of our next events again. Hopefully hybrid and or physically next time.
Good.
Great.
Looking forward to that.
Then
Thank you
have a
very
nice
much.
day in Munich, and bye-bye.
Thank you. Bye.
Bye-bye.
Thank you. Bye.
Bye-bye. Have a good day. Thank you. And Clemens, we have a short 2-minute break. And after the break, we will discuss low power in AI sensor applications with an amazing company based in Austria and many other countries, AI Storm.
Yeah, see you after the break. So, and we are back with the second keynote in the morning session. Yeah, I mean, in terms of agenda planning and logic, we, on the one hand side, we had this, as Mr. Altenmüller has said, a company that exists for more than 100 years, although not 100 years in the semiconductor space. It's like the established European industrial player. And now we want to basically, from the other side, look at a very forward-looking technological approach, which is edge AI and in-sensor AI. And for this, we welcome Mr. Andreas Siebray on the stage with us. There is a problem with your microphone, Mr. Siebray, I'm afraid. No.
Yeah, maybe we have to try and change the microphone to a headset. And I mute you for a second. Yeah, so let's try that. Okay, now we have to change the audio settings there's a little cogwheel down at the bottom of the screen where it says cam/mic. All right, and there you have to pick another microphone. Maybe let's try that.
Is this working?
Oh, now it's perfect. Now it's perfect. Mr. Siebray.
So I can get rid of my headset again. Okay. Okay.
Yeah.
Thank you very much. Good morning, everybody.
Morning.
Good morning. Yeah, Clemens already did the intro. I would say I think you have prepared some slides for us, and we will hear your presentation. And all our viewers on LinkedIn, this is live, so use the opportunity to ask questions and to interact, and we will answer them together with Andreas Siebray, worldwide VP at AI Storm, at the end of his presentation in a couple of minutes.
Okay. So let me share my slides. So, do you see my slides?
They are coming up, I hope. Not yet. So in the meantime, the disclaimer, you can follow us and AI Austria as well on LinkedIn and on Twitter to receive further updates and to stay in touch with the community.
Okay.
And
Now the screen share works.
Okay.
Perfect.
Let me just quickly pull them up. Good.
Okay.
Mr. Siebray, the stage is yours.
Okay.
We see your slides.
And see you in the Q&A session.
Yeah. Okay, thank you. So our company is called AI Storm. So we were founded 2018 in the US and here in Graz. And we start to develop a completely different approach of AI. So we did all of the calculation instead of digital or analog voltage or currents, we did this in charge domain. So charge domain has quite some benefits and has also some up and downs. And I want to go into this and want to visualize what we are going for. What you see on this picture is that our first work, what we are doing right now, is trying to use AI for always on and for intelligent always on in IoT devices using super low power or lowest power possible. So what means charge domain? In usually digital contents, you are calculating with your accelerators. You are calculating different inputs. You have to divide down the inputs. You have to sum the inputs, and based on an activation function, you send this out. So what we do in the charge domain is that we don't handle the signals as a digital content or a voltage or a current. We are handling this as a charge. So what we are doing is we can accept different input charges. So here you see up to n input charges what we are using. With this charge, without changing the contents, we could divide down the charge level, and we could sum the charge. And based on the sum charge, based on an activation function, we could send this out of the engine again. So this is a complete different approach, because here we don't talk about how many bits we have, because we could scale the bits. We could scale also the weights with different contents. And yeah, on one side, if you look at this, it's pretty close to the human brain, because we have electrochemical transportation and calculations in the brain, and here we are just doing this with charge, and then but on a controlled manner. Yeah, so this is the big difference. Yeah. So the advantage of compared to other analog behaviors or solutions is we have no RC time constant, because a charge you can move. You don't have to load a cap, or you don't have to establish then a final set of current in order to move then your information. You just move a charge from A to B. Or when you move the charge from A to B, you could reduce the charge, which is a divider function. So this means that we have a constant charge time operation based on a system clock. So it is not the signal transformation is not based on the amount of charge or on the amount of inputs. We can directly clock this through. And for an operation like n inputs, so just multiplying all of these inputs, summing this up, and sending this out, we need 2 clock cycles only. So compared to a digital solution, for the digital solution, well, we have then 4 bits, 8 bits, 16, 32 bits. Then we have to do always the operation that we have the input signal over the weight. We have to multiply this. We have to add this to the sum and accumulate. And for digital, the problem is for n parallel inputs, we need n parallel engines, which is scalable, straightforward. But this engine has to feed in n half parallel engine, and so on until you reach a single output. So you directly can see the clock count is not comparable to 2 clocks for a standard operation in the charge domain. So this is a significant reduction of clock cycles per operation. And the unused structures for this is a second thing, because if you build this system up in the digital part, you have an accelerator which is hard-coded, and you cannot just change the number of inputs and you get a faster processing time, because if this is hard-coded, you always have to clock through the whole thing in order to get your single output, even if you load this Mac with just a very small amount of inputs. So what I show you here is just a pretty nice paper from IBM Research Center, which was published in 2019. So what they came up with is if you're using these digital accelerators and you're downscaling in the process nodes and you're updating the algorithms, so you could enlarge your computation speed and the complexity quite a lot, but at a specific point of time, you are limited there. And then you have to go to digital AI cores with approximate computing. And the next level would be analog AI cores, and then analog AI cores with optimized materials. So comparing this to the possibility what we have using charge domain computation is that we can break out of this line. And so what I see over here, we start with the digital accelerators, then we have analog AI accelerators. The next step in speed, what is possible, could be charge-based accelerators. And at the end of the line, if we go to quantum computing, then we are still in the size of super tiny charges, what we are moving forward. So charge domain is not something very out of the box. I think this is fitting in this development line. So having this charge domain mix, how to form a network. So what you see here is just for object detection, it is a 32 by 32, could be an image. And then in order to come up with a 10x selector, we can use this fairly small image processing in order to detect then 10 different results. So, but when you look at this, you see for taking the image, if we use a 3x3 stride 2, then we would use 32 filters. So if we have this NMAC with 9 inputs, so 3x3 plus 1 bias, I could run 32 of these structures in parallel, and I could just load the weights just once, and I can go over this picture, and then I'm producing 32 pictures 16 by 16. So this could be done with a single engine. If I do an 8 by 1 by 1 by 32, so I'm running 8 filters right now, and I'm doing a depth-wise convolution. I'm generating a 60 by 60 with 8 pictures. I could use for here an optimized, or the second MAC structure, which is 32 or 33 to 1. So 32 inputs plus 1 bias to select for optimizing. And then I could achieve the second step. For the third step, I could already reuse the first neurons. I just update the weights, and I could run then 16 filters instead of 32, so I would need half of the engine. And I'm running and I'm getting an 8 by 8. So if I go this through, you see, I would need a 3 by 3, which is a 9 input. I would need then a 32 input. Here I would need a 16 input, and here I need a 512 and a 64 inputs. So if I would design just a Mac like this, I could directly run this without looping the signals, without storing data in between. It could go straight through. And the advantage of this structure, as I said, is that we could scale the Mac topology pretty easy. And the Mac reusage, what you see over here, so instead of having for all inner layer a separate structure available, we could recursively, we could run the whole thing and just have a virtual number of Macs, what it's needed for any network. We could reduce then the size to the physical quite a lot. So going to the IoT, we are working with quite low battery life, because IoT usually means you have a sensor somewhere in the field. It has to be always on, and then you want to have a wake-up event, because whatever you're doing with a sensor, usually you have an always on to have an intelligent wake-up. And after the wake-up, you could then run quite some higher computing algorithms later on. But these are running so seldom that you are not draining the battery by this. So for the always on, this is usually the very critical point for battery lifetime. So here it's, for example, you have just an imager, and you want to make a wake up on object. So you can make, I have some examples later on. And here you see we have a pixel array. So the standard solution would be we have a pixel array. 3T, 4T, 5T pixels usually are in the voltage mode. So we have to wait quite some time until the voltages are established. We have to digitize this. We have some sorting function, and we have to prepare then RGB and everything per pixel. And then we are going out. We have a serial deserializer. We are going to a remote AI. So all of these steps takes quite some power. So the whole chain is then the overall thing which is draining our battery. So our target is to remove most of this and trying to make the AI computation, which is doing our intelligent wake-up directly inside of the pixel. So this means when we have a pixel array, instead of reading out the voltages out of the pixels in the standard manner, we can directly read out the pixel in the charge domain, where reading out the pixel is already our first layer of the AI. We could scale down the AI engine, and we only have to send an event, which is well, it's an adult, it's a man, it's a woman, or it's a children, or it's a dog, or it's a cat. So this way, we could significantly put down the power dissipation, which means that it has big effects then on battery lifetime and also on the complexity on the system. Okay. So how does a charge domain input layer work? So if you're familiar with a pixel where we have a photodiode, which could be a pinched photodiode or a standard one, inside of the photodiode, the light is just captured during the exposure time, and it's stored inside of the photodiode. So this is not like a capacitor, which the voltage is growing or something. This is just a charge where we have a constant potential, and just the number of electrons are rising. So when we take these out, usually we take these out with the same mechanism to the voltage based. So we are charging an external capacitor, and then we have to wait until the whole thing is stabilized. We have to convert this into a lower impedance signal, and then we have to ADC the whole thing. So being in the charge domain, we could directly use the amount of electrons which are performing the charge directly in our first layer. So the first signal capture is already the first layer of the AI, because we are feeding directly from the photodiode the charge over spill and fill to this layer. If we are going to different sensors, then it has also a lot of advantages, because if we are looking for fingerprint, this is still in it's like a pixel. So this would be the conversion what I'm talking about. If we look for biometric or gesture, then we have usually an analog signal available, which we could directly convert from a voltage or current into the charge. So the ADC and the waiting time and everything is not needed for this. For voice, we have a setup that we could directly connect to a MEMS membrane in the charge domain, and for phase, this is imager-like. Yeah. So this way we could make it happen that the sensor input signal is already our first AI layer. So there is not all of this signal handling needed upfront. So when we are looking on an imager with always on wake up, we could you see here on the left hand side, you see the imager. So what you see here is we are directly connecting then the pixels. The pixels are performing the first layer, and from the first layer we are going then to the side located rest of the AI engine. The advantage of an approach like this is we don't have to pre-process the image, because we can make the decimation of the image directly inside of the first layer. So here we could run super low power, because when you look at this, we could run with a low resolution of the imager, and we can say what can we detect over there. So if we detect no phase, we stop the whole thing. If the possibility for the phase detection is over there, then we are reducing the decimation, and we spend a little bit more power and getting more pixel information to calculate to AI in there. And so we can do this by steps until we get to the maximum resolution, and we can get the final decision in order to start up whatever system is sitting behind. So this way we could really having stopping points in terms of power dissipation on different power levels, which significantly can reduce then the battery lifetime. And the whole thing can then be used then to detect quite other signals, because the same approach could be used then for fingerprint, face, gesture, person, or behavior. So everything what you want to do as an intelligent wake-up could be handled by this. So our first product is called Mantis AI in Imager. So what you see over here, so we have the C100A. This is our first chip called. So we can control this from the outside. So we could have then on the IoT, we could have a radio. We could have then the application microcontroller with supporting additional cameras and higher power operation stuff. And we could also feed from the outside signals in to use the wake-up processor. So here we have Imager LED driver AI processor and the complete programmable control inside in order to do object detection. And for object detection, if we just go in the household, there are quite a lot of possibilities. So we could have a TV control to prevent kids from seeing the wrong contents. We can make remote control keyword spotting. We could have quite a lot of things on safety. So glass break, magnetic replacement, so IR beam replacement that we do instead of a pure IR beam wake up. We can make a wake up on object or on face to reduce then the total power dissipation. And inside of the house, it's quite a lot. For example, object occupancy detection, or the doorbell, for example, wake up on items of interest. So if Amazon is coming with a box, then we can detect, oh, there is a box, so we have a shipment and things like this. On the downer side, you see then also the possibility to do people counting, because based on how many people are in the room, you can control the complete environment like AC, lighting, and temperature control. So this is our first Mantis product. This product, what you see here on the top end side, we have then the charge domain engines. These are these boxes what you see. We have the control around. In the center we have the imager with the controller, and then we have some memory inside, which is just SRAM. So what you see here is our lab settings. So what we can do over here is we can then doing the image capturing, and then we can calculate the wake up on object. So you see is we are downscaling the images quite a lot, because this gives us lower power operation, and with this optimization of the image, this is best to fit into an AI engine. So can you please show this short YouTube video now?
Yes, we are pulling it up.
Thank you.
And here it is. Do you want to talk over it, or should we play it with audio?
Just play it with audio. I think this is self-complaining. A colleague from mine is doing all of the comments. So I don't have to comment this in addition. Yeah.
Good. We start now.
Thanks.
Let me introduce the Mantis development board we are using for the following demos. With the Mantis chip on it, we are connecting through the USB interface to the computer and running some basic AI tasks on it. The next demo is raw resolution phase classification. Some of the samples of the dataset are seen in the screen. Again, three fully connected layers were used. The TensorFlow model evaluation and the chip execution is running parallel, and the results are printed on the screen. The two outputs of the last layer are printed, and the first number is belonging to the non-phase class, and the second number is belonging to the phase class. The predicted and the true labels are also printed. Here 0 stands for the non-phases class and 1 for the phases class. The execution was finished, and we can see that 99 out of 100 samples were correct. The next demo is low resolution phase classification. Some of the samples of the dataset are seen in the screen. Three fully connected layers .
Yeah, I think there is unfortunately a hiccup on the StreamYard side with showing the video. If you could provide us the link, Mr. Siebray, we will post it to the chat, so afterwards everybody can watch it. And when we afterwards release the video on YouTube and LinkedIn, we will make sure to have the whole video included.
Okay, I will do so. So unfortunately, this I thought it was just on my screen, the hiccup, but it was a general thing. Okay, so I will support the video and share the link. Yeah.
Please, yes.
Okay. So I have to continue.
Exactly. Yes. So you have to reshare the slides again.
Okay. So sorry for this. That was not planned.
We have to be sorry, but we can always blame it on the cloud and the tool, because we are like powerless if this happens.
Okay, good. So yeah, the demos show you that just with this is a 96 by 96 imager that just capturing the image, feeding this to the AI, we can do then face detect. So all of this AI hardware is nothing if there is no software about this. And I think nearly most of what we heard these days about AI is software related. So what we put together, so having not just a digital computation as we have a charge-based computation, it's we had to update the stream, but at the end of the day, the whole thing is running on TensorFlow. And we are doing a little bit more than the standard one because we are doing pruning, weight sharing, and we had modified activation based on a charge domain engine. Yeah. So here we are supporting a standard flow, a standard software flow, where we could accept then all kind of user inputs with training data. We can emulate on the PC all of the optimization, and then after the output is good enough, we can just compile, send this then to the hardware, and we could make then some final hardware runs over there. So right now for our wake up scenarios, so we have initial release support for tiny models for keyword spotting, command word spotting. Then we have tiny models for intelligent wake up, also with binary connect, and then for person and object detection. So examples what we have run in our simulation already is we could have a GRU LSTM expansion, word wake up and control. We did quite some MobileNet v2 variants for word wake up and control, mobile FaceNet. We did some variants, then binary connect for cascaded wake up, and variant for cascaded wake up, MobileNet v2 SSD, and TinyYOLO. So this is our demo board. So what you see is just the camera, and that's it. On the back side, we just had a small controller and an interface, and under the lens you see then our chip. And what you see is this standard wake up. What I showed before is just on the left-hand side. What you see is we are using also then 3 different setups of the AI structure of the charge domain engine, which is optimized more than to run then these specific tasks. Applications, what we have detected, they are endless, because in terms of industrial control, there we have tons of operation. Then accessing for enterprise IoT, for consumer IoT, we have the smart home. I showed you some pictures. For mobile phone is, for example, wake up on face, wake up on gesture, and all kind of stuff is possible using this. And for the variables which are extremely power sensitive, we have then detected the smart eyewear, visual health monitoring, etc. So that was my phone. Okay, to summarize the whole thing, so the charge domain is enabling us for quite low power and high performance operation. The whole setup is scalable, so we are able, even on very old process nodes, to run this AI, and for better performance and higher integration, we can downscale this. So we could even make on 90 nanometer or 180 nanometer wake up on object. So what we have based on this, using the first layer of the imager, directly in the charge domain. So we could have super high frame rates, so up to higher than 50,000 frames per second for low resolution cameras. Let's say in the area of 200 by 200 pixels, we could even go to 100,000 frames per second. On the always-on power, so this this product, what you see, so we could go down to around 15 microwatt with no polling delay, always on, and capable of performing high-speed extraction only of items of interest based on charging pixels or smart recognition pattern matching. We have then smart driven capabilities such as wake up on word or wake up on face. Then we are supporting the industry standard tools such as TensorFlow, and it's compatible with standard neural network configurations or neuromorphic spiking approaches. On the MAC efficiency, so currently with our setup and what we have today, so we see the high performing MAC limits is up to 4,400 TOPS per watt, which could scaled up that we could have a system efficiency up to 200 TOPS per watt based on the application. We have this situation gives us, or this charge domain engine gives us also the possibility to have low cost AI, because running this at older lithography nodes gives us an advantage, or it would give us the same cost in the same process node compared to standard AI, but much faster execution time. And we have no input digitization. So therefore, we could integrate the sensors such as pixel or audio MEMS membrane into pre-processing or neural network input layer. So thank you. That's the end of my talk. And I'm open for questions.
And we have received a couple of questions. Thank you for your presentation. And definitely, let's make sure to share the video that didn't work with the audience later on. Maybe you have a link. But first, let's look at the questions.
Yeah.
Yes. So, what questions do we see here, Clemens?
The first one is regarding noise and distortions.
How do you manage input noise distortions?
You see, the point is compared to standard switch capacitor solutions, we always have to we always working then with a fixed voltage or with a fixed current. By putting the charge into this, so I'm not relating on a fixed voltage, I'm only relating on the charge. And the charge handling, so we made some calculations, so we came up to about, this was about 3 to 4 microvolts absolute noise, which gives us an accuracy of over 8 bits. Yeah. So our target is not to make 8 or 16 or 32 bits. We have structures for this if a higher accuracy is needed. Then we are splitting up the engine, but for a single engine with a single charge fill, so our limit is up to 8 bits.
Mm-hmm. So the limit is 8 bits. And the next question I see here on my side is from Pedro. What is the size of a neuron on a given technology?
Okay, so this is quite. It depends what kind of neuron, because the neuron is based, or when I design a neuron, it's based on the number of input structures. Yeah. So if I do a 108 inputs, or if I do a 9 inputs, that's quite different in size. The neuron is fairly small. So right now, I will not disclose the numbers directly, but it is compatible, or it's even dense compared to a digital solution. This is what I can say. Yeah, because for the digital solution, if I make an 8-bit placement, I'm smaller with the charge domain part.
Fantastic. And a question I see here now is from Dietmar. How does the machine learning pipeline look for this chip? So he asked that during your presentation.
Yeah. So I fairly showed a little bit. So we have an emulator on software, and we have to do pruning and also reducing then the data sets and all of this stuff. So this is we have to do a little bit more steps like on the standard digital approach. Yeah, because the flow and everything is given, and it's optimized, and everybody's just using this. So we had to develop our flow, and we have a fixed set of loops what we are doing. So whatever we are doing, we just reuse our engine. But we have optimized an engine, and it is, I would say, it's the layer under TensorFlow is always depending on the accelerators you're using. And based on this, we have to do our optimizations, which we did.
Thanks. Hope that answers the question of Dietmar. And just a question from Martin came in. How do you define your operation? Is it an 8-bit Mac? Can you disclose it?
Yes. Okay. So our Mac is scalable. Yeah. So usually the problem is if you do a CNN, then not every layer needs the same accuracy. Yeah. So based on your structure and based on your internal flow, you need different accuracies. So we are running or we can run some Macs 8 bits. We can scale them down. Or we could also split it up to go then to higher than 8-bit. But this is then a different structure, and this is a little bit bigger. But you see, the big advantage is it is not a single structure because it's scalable. And therefore, based on the needs, so we are really checking then the required accuracy layer by layer, and therefore we can make this optimization.
Thanks. Clemens, on your side, do you have more questions?
I don't have a question, but the previous keynote speaker has a rather lengthy question. Can you read it, Mr. Siebray, or should I read it aloud?
I'm just starting to read. Okay. Yeah. You see this. I see your point. So this is exactly the point why this charge domain AI is so interesting, because we can even make AI in 180 nanometer. Yeah. So therefore the state of the art image sensor. So it was 65 nanometer. It was scaled down to 55. Right now. One big vendor is running 40 nanometer image sensor technology. So therefore it is directly scalable. And we have a setup that we could run with 65/40, or we could run with 55/40 nanometer. Going from 40 to 28 nanometer is optimizing then the power performance and the scalability. But for our target, what we start up, because you see, we started our company 2018. So the first level was to make intelligent AI directly in the sensor with super low power, and therefore we don't need a very big AI. Yeah. So this is why we started with quite an old technology, but we do have already some. We have the work running, then going down to 40.
Okay, just when I wanted to say we're done with the questions, another one comes in. This is like the last one I would take from the audience before the considering the decreasing of the neural network. How big is the trade-off considering accuracy or other metrics?
So our charge domain engine is completely freely scalable. So we are not limiting on enlarging the charge domain engine, because we have at a specific size, based on the digital control, we can size this up. So we are not limited like on analog approaches on a specific size of analog, and then we have to stop, because then it's getting unaccurate. So the accuracy is dropping then. So our accuracy is directly inside of the charge domain engine fixed, and based on this, we could just take this from cluster to cluster and then scale. So this way we can scale the clusters up. Yeah. So we don't have a physical limitation on scaling here.
Great. Then, yeah, I mean, we will meet later again in the first session in the afternoon on the podium discussion. So I don't want to spoil too much, but I would have a question regarding your company. You mentioned the company was formed in 2018, and you are the worldwide VP for design. My question would be, how big was the impact of COVID-19 and the travel restrictions on your product development process?
Well, using all of the virtual communication channels, we did not have so much restrictions. I would say the biggest restriction was not being able then to travel to our reference customers and to visit the foundries. Yeah, so this was a big trade-off, and this was delaying quite a lot of the development cycle. Yeah.
Mm-hmm.
So inside of the company, usually it's not a problem. The problem occurs to the outside, because for very sensitive topics like what we are doing here, you really have to show up face to face in order to clear the contents.
Mm-hmm. And you also have quite the distributed team. I think you mentioned it shortly in your introduction, but you're located in Austria and in several places in the US.
Yeah. So you see, so the core R&D is here in Graz, in Austria. Mm-hmm. And we do run design centers in Budapest. And we have a design center in Rochester, which is popping up. We mm-hmm. have our headquarter moved to Houston. Mm-hmm. And we have some activities also in Florida and in Taiwan, in Taipei.
Exciting.
So this is our current setup right now. It's more planned. We are growing. We have our Series B already done, and now we are really focusing then for the next round.
Perfect. Yeah, I will drill you with more questions in the afternoon. I prepared a lot. Okay. So thank you very much for this overview. Yeah,
we will welcome you back later in the afternoon.
Thank you for the possibility to have this talk.
Yeah.
Thank you.
Thank you. Bye-bye.
Bye-bye.
So, and yeah, before we start in 5 minutes at 12 a.m. sharp, we will show you a brief announcement of the next speaker, this time not with a video, to make sure that none of our computers or neither the cloud is crashing. So see you in 4 minutes at 12 o'clock.
Stay tuned.
So, and we're back with the last talk of the morning session today. We started with an established industrial player, followed by all standards, very large Series B AI chip design startup. And now we draw the wheel even further with a relatively new startup, which is still in its seed phase. So with me on the stage, I welcome Nico Terringel from Danube Dynamics. Hello, Nico.
Hello, hi, Clemens.
Who will, in the next 20 to 30 minutes, provide you an overview about AI, or let's say edge AI for industrial applications. And yeah, it's also actually a funny coincidence because in the afternoon session, I will do the co-moderation together with a colleague of mine from AI Austria. It's Dr. Dietmar Millinger. And Dietmar was your professor at the University of Applied Science. So it's funny that there's also a connection available here. This is actually how we found you.
So this is going to be a defense. Yeah, just the next round.
Excellent. So yeah, with this, let me see if the slide sharing is working. Yeah, excellent. With this, we hand over the stage to you. As always, this goes to the audience. If there are any questions, please post them directly on LinkedIn, and we will take them one after each other from there. So, Nico, the stage is yours, and see you after your talk.
See you in a bit.
Thank you. Thank you very much, Clemens. Yeah, hello, everyone. Thank you for tuning in. My name is Nico Terringel, and I'm the CEO and co-founder of Danube Dynamics. And with this presentation, I will try to give you an insight why we think that self-learning industrial machines are the future for industrial manufacturing and smart factories. I will also tell you about our technology and about our concept to achieve this goal, and which obstacles we already experienced and how we plan to overcome these. Yeah, let's start with a short introduction. A short timeline of what happened already. In 2019, we created the idea of edge AI computing from our studies at the University of Upper Austria. We come from the area of embedded systems design and very hardware dependent software development. And combined with the AI knowledge we already gathered in our bachelor's degree, we had the idea to combine these two areas, strong hardware-dependent software development and AI, in order to create the value for industrial purposes. And in the beginning, it was not clear for us that, or what was the actual use case, of course. But as we already gather experience in some industrial companies, we began to wonder why there are no smart solutions for these factories already in the market. Because when I first saw such a factory, when there were like many workers programming and working with these robots, and I asked one of the leads there if the robots can handle any of these objects independently and automatically, or if they need to be reprogrammed and or if this all functions automatically. And they told me that it's not possible at the moment that these machines completely work autonomously, and that they need a high collaboration with workers. And there are also some special people in all these factories which are only there for like reprogramming and telling the robots and machines what to do. So that was the initial thought and idea that we should take our knowledge and bring it to industry. And in 2020, last year, we then founded our company. First of all, with the idea of developing high quality embedded systems. And after we have seen that there is a potential in the market for us, because we've done some interesting projects with industrial customers, and they were really satisfied with our work, and it strengthened our our site on ourselves, so we can do much more than just services and development. And in 2021, exactly in the beginning of 2021, we started to develop our own solution, which I will explain in the next slides. And our plan is to create our first proof of concept prototype for our early stage customers and partners in Q2 2022, and market launch should be in 2023. Hopefully this development goes as it's meant to be. On-machine intelligence is achieved in our thoughts by three major components. The first thing is, of course, state-of-the-art machine learning algorithms. And I have to say that there is a strong evolution in machine learning all the time. But in the last years, there were some really interesting aspects, as we are a little bit shifting from the big data thing to like small data, and training models through less pictures. And that was for us the opportunity to use these kinds of algorithms in industrial purposes, because you have always like the problem that there are too few data sets you can use. But I will go into deep afterwards. The second thing is custom hardware and chip architecture. As I already told, we come from the field of embedded systems and also have a strong FPGA background. For those who don't really know what FPGAs are for, the afternoon session with ICE will also go into deep with this technology. Basically, it's a hardware architecture. It's a chip you can reprogram to do any task you want it to do. And all this happens directly in hardware. So there's basically no software involved, which enables some really cool features I will tell you about afterwards. And of course, for us, a very, very important aspect is the industrial grade communication interfaces, because the thing with all the software-based gadgets are that they don't really have the opportunity to communicate with those highly real-time controls in the industrial area. So you have to really get close to the point where the machine actually is, and have a strong real-time communication with these machines. And all this combined in our own solution, which is mainly a hardware software solution. But it's also, we provide IP, but we also have the ability to provide full compute models to our customers. So we're not ready to really strengthen our business model. We're also trying to try out things. What does the customer need, and what is possible for us to provide. So we're a little bit of a search for a path, for a concrete path, and later on I will ask for a call of action, because we are currently searching for partners which can provide us with use cases, and where we can implement different types of use cases and products together, because as we all know, industrial area is pretty hard to get in. And so we're trying to make some contacts in this area to provide for use cases. Possible use cases are basically all types of industrial robot arms, of conveyor and belt systems, and also high bay warehouse systems known as smart logistics, where machines basically slide through all the high bay warehouse houses and try to recognize which wares are in there, and basically it's a fully automatic warehouse thing where this technology can be used to recognize objects in real time. One of our use cases with one of our first stage partners with Keba AG, it's a big industrial automation company from Linz, from our hometown. And this is basically our first use case. In cooperation, we realized autonomous intelligent robot arm. And the thing was that the robot arm can automatically handle different kind of fruits and sort it from one box into another, fully automatic. And the big thing there is that it can also learn new objects independently. So you tell them, you robot, there is a fruit you don't already know, so please learn it. Then it takes like several minutes, 3 to 5 minutes, and the robot can then again handle this new object automatically. Some interesting things about robot arms in detail are the independent path planning. So it's always a critical thing that you get the information you get from the model is basically the coordinates from the object, and from this information you have to come to the final path where the robot is actually moving. That's also very critical. And also the grasping itself is an important thing, but all those things were handled by Keba because they're really good in these things, and we have basically done the AI computation and all the pre-processing, post-processing, and communication with the Keba robot control. So that's one of our example use cases, and that's basically a short introduction what we're doing. I have to say that, as Clemens already mentioned, that we're really early stage. I think that the technology has a big potential, but it's also very critical for us to get further use cases and get more into depth with industrial partners. Otherwise, it's a little bit challenging for us to find real use cases for a technology which has a real broad range of applications. Then I have to tell you, or why do we do this? Asking for the why. It's for us, it's always a really important question to be answered, because there are many technologies on the market, and especially in the last years. For example, everyone knows NVIDIA, edge computing devices, and many others. It's always important for us to ask the why. Why do we do this? Why do we need intelligent and self-learning machines? Why do we need cloud independence? This is very interesting because on the other side, the big difference between our technology or our concept is that I simply connect the machines to the cloud. That's what most of the companies do in the first place, because it's simple. It's very simple because all the software side on the cloud servers are already done by machine learning experts, and I simply have to connect my machines to the cloud. And here we go. And this question I want to answer. And why do we use FPGAs in the first place? I think that's a very important aspect, because FPGAs are pretty special in terms of their architecture, in terms of how they are programmed, and how do you develop FPGA applications. And I think it's a good first standing point connected to the presentation from ICE in the afternoon session. And these three major questions I will hopefully answer. So let's start with the question, why do we need intelligent self-learning machines? Of course, the rate of automation is currently rising, and we believe that in the future, in like 7 to 10 years, probably factories need to be autonomous, because if you think of such a heavy labor workers who do all the work machines can also do. Another aspect is that the efficiency of such factories can only be incremented if the grade of autonomous operation is higher. We cannot simply put more industrial machines together if they're not working smart, and if they're not connected together, and if there's not some form of interaction between humans. But the thing is that with current applications, there is so much work to do by hand basically tell the machine what to do, that we won't reach this level of automation if we don't have such self-learning machines. Yeah, as I already told, robot programming is labor intensive and also error prone. It's very critical to companies. We've talked to some of our partners and customers why they in the first place need such machines, and they always tell us the same thing, that this interaction and programming aspect is really critical to them. So with such a self-learning machine, this would fall away for the companies as a potential risk factor. And especially when interaction is necessary, there's some aspects in cobots, I think it's called, that the interaction has to be more interactive. So the robot has to recognize the human, and so they can really work together efficiently. And if the robot is only doing his thing, or only doing the same movement over and over, and is not really sensitive to its surrounding, we won't be able to get higher efficiency grades at all. Optimization and automation of workflow is, I think it's implicitly, as I told, that we have to get a whole new level of automation in order to optimize the workflow. Summarized, we can say self-learning machines helps to reduce costs in many areas. As I told, in the area of programming the machine, and also in the productive work when they work together with humans, it raises the efficiency level and reduces costs. Why do we need cloud independence? That's a very important question. For most of the companies, the data they gather from their machines is very sensitive, very important, and what they told us is that they really don't want to give data outside of the factory, because the fight between companies, or let's say the fight over data, is getting more and more serious, because the data is so valuable that it would be pretty bad for companies to lose this data. It's a task which is not really simple to do, because I only have 2 opportunities, connect to the cloud, and my data is away, because in the end I can't really control where my data is going, because there are only several possible cloud infrastructures available. And the other thing is that the overhead in data transmission is really big. So we might face a big challenge in future when we're not able to process the data where it's originated from. For me, it's a personal aspect, because we think that in future the ecological aspects get more and more serious, as we already know that our Earth is running out of resources. And I strongly believe that with our technology nowadays, we're able to face this problem properly. Of course, the technical side is also very critical, because communication with cloud takes more time, of course, and is safety critical, because I'm always dependent on the cloud infrastructure, and it's also very, very expensive. Cloud infrastructure is critical and expensive, and in most applications, or in many industrial applications, I simply cannot use certain cloud services, because then my machines won't run at all, because real-time aspects are not handled anymore. Of course, the safety aspect goes one step further, with avoiding harm to workers. If the system cannot handle such situations by itself, and simply has to ask the cloud what to do, then it might be too late. As I already said, the downtime of a factory, of a plant, is also very critical. And with such edge computing technologies, you have the possibility to massively decrease the possible downtime of factories. It's not the plant downtime; it's always like the unplanned downtime that costs you that much. Summarized, we can say, to increase security, safety, and facility uptime. That's the important aspects there. And last but not least, I think the most interesting part is, why do we use FPGAs? Let's start with the basics, with the basic architecture. As I already told, FPGAs are used because of their flexibility, because of their flexible hardware architecture. You can reprogram these devices, these chips, during runtime, and calculations are basically done in hardware. So there are many little switches, like transistors, who are connected together and calculate different things you tell them to do. And the most important aspects with FPGAs is definitely less latency, more throughput. What brings us back to the AI topic, because with Edge AI, I always have two goals. I want less latency in predictions, so one image or anything else to be predicted needs to be very quick. And on the other hand, I want a high throughput. That means I want to calculate as many pictures as possible at once. I mean, the same thing is definitely the thing with GPU-based systems, but FPGAs are really good for doing such kind of calculations. Scalable and flexible is really nice, because you can basically take any FPGA size you need to use for your calculations to be placed and to be executed. And you also have the possibility to switch through architectures during runtime. It's called reconfiguration. Another thing is partial reconfiguration. It's very interesting, because you can also reconfigure these devices partially, which means, let's say on the one side of the device, you have your AI engine, and on the other side, you have your real-time communication interfaces. And maybe I want to exchange my AI engine with a better suitable one for such kind of applications. You don't have to switch the other part, so you're really flexible. And for our business case, or for our technology, it's very important, because we have like two different processes to be approached. The first one is the runtime itself, the inference. So I want to predict objects, I want to predict images, and we have like one architecture which is optimized for low latency and really high throughput. So you try to utilize all resources which are available in your device, and try to get as much performance as you can. And when we switch to the training mode, when the machine learns by itself, we switch our architecture, and then we use an architecture which is optimized for high accuracy and low training time. That's a basic thing, because when I'm able to switch the basic architecture, I can optimize in a whole new level. The other thing is, when I'm only optimizing in the software side, I'm much higher in the whole stack, and the increment is much less compared to hardware architecture optimizations. For us, also very important is the industrial purpose, because we get asked a lot, why don't you use standard NVIDIA GPU based or Google TPU based accelerators? And one important thing is the industrial usage, because with FPGAs, they're mainly used in military, industrial, aerospace, defense areas. where they are really strong because of their robustness, longevity, their long availability of hardware parts. Also very important for us is, as I already told, the real-time communication with machines. So you basically have the ability to implement nearly all kinds of state-of-the-art real-time industrial communication interfaces. One example would be OPC UA TSN. So we don't have to put like many of them on one device. So we can switch through interfaces depending on what our customer needs us to do, and that's very clever, because you always have the challenge that different plants, different machines, and so on have different requirements on communication. And so I only need one device and can address many different use cases and applications and controls. That's a very nice feature. One thing is the deterministic behavior real time, as I already told a few times. This goes hand in hand with security and safety features. Basically, in industrial plants, you always have your security and safety critical applications. You have to meet standards and criteria. And with execution hardware, I basically have a much easier approach to implement those security and safety standards. Let's say there is an application which tends to output the result in 50 milliseconds, but the machine is told to stop in a time frame of 10 milliseconds if there is some state of error. And if I use a software-based system, maybe there are some latencies because of interrupts and other things happening in the system, and we can basically implement those security and safety aspects directly between or directly in our chip in front of our AI engine. So it's completely independent from all the other calculations. So there is basically no latency, and we can react to those situations very quickly. And as I said, in a deterministic time frame. What are basically the main challenges with FPGAs? I think that's also very interesting, because it's not a common technology, I think, for companies. The software-based approach is, of course, not that easier. Let's say it's more complex, and it's higher risk and more costs are involved. So maybe some of you are not really haven't been really faced with FPGA technology, and we try to summarize the main challenges we've been faced already, and we also know everyone is been facing with when trying to use FPGAs by itself. But let's start with the challenges with self-learning AI. The thing is, as I already told, big data sets were used previously to train big models, and this was no problem, because the access to data was nearly unlimited. And now with such use cases like industrial machines, you have the situations that there's not much data available from our project and use cases. You can say that there are between 50 to 250 images available for one object. So the robot takes some pictures from the unknown object, and that's everything you got. So that's one challenge you have to face. Two aspects which are also very critical is retraining time and accuracy. Of course, when you have few data available and also few time available, these two aspects are very critical, and we try to face these problems by using new algorithms like few-shot learning and transfer learning. It's also very known in the field of machine learning. But what's new is that our process is or how we see the process is that inference needs to be very quick, and then we switch, and in most cases you have like 3 to 5 minutes. In this time you have to learn the new object, and after this time the machine has to pass on and run in normal mode again. So we face this problem with retraining time with special model architectures. So very interesting is that there in the last years there were some pretty big steps forward what's in aspect of accuracy and retraining time. So with new model architectures you can really train objects very quick, and also the accuracy can be very good even if you use few images. One of our examples is that we try to recognize crews, and interestingly, some of the tasks a AI model is executing are pretty easy for us humans to recognize. But in this special use case, we tried to predict or to recognize very small screws, and our new AI model architecture was able to also differentiate between screws that were really exactly for us humans. And I think that's pretty interesting because I think, or maybe in the next years, the machine learning models get so smart and so good that at any time, at some time, they will challenge us humans. And I think that's where it gets interesting, when models get really so good that you can use them for purposes where a human could not even challenge them. Then also interesting is computer resources. I mean, it's very clear to us that when we go from cloud to edge, that there is limited resources available. But not only the resources in terms of computation, but also that I don't have the flexibility with software systems, that I can switch through models at any time and use different algorithms, because everything is already programmed in software. So we have the challenge to, when we want to adapt to new architectures, we sometimes have to change our hardware architecture too, and that's of course a pretty high resource task. One thing which is interesting too, I think, is the term catastrophic forgetting, which means when you learn new objects, you start to forget the old ones. That's one thing that we also currently face, and we haven't really solved this problem. We're trying out some optimizations and some algorithms on this side. But that's one thing someone has to really think of in his own application, because it's more simple, like, to learn new objects, but then on the other hand, if you forget the old ones, it might be not good for the machine process at all. So now to the main part of FPGAs. With FPGAs, you have, of course, a much higher development effort. That's why most of the companies are not really interested in developing architectures for FPGAs. The whole difficulty lies for me in the combination of knowledge. So in our company, we're glad that we have a strong team which both knows AI in detail and also FPGA architectures. But for most companies, it's pretty complex to combine these two technologies, because the one thing is absolutely software driven and mathematically people who are really experts in AI. And on the other hand, there are some hardware experts who came from electronics at once, and to combine this knowledge, there are some special challenges when you stick them together. And also the economic risk is pretty high because the thing with FPGAs is that the development flow is pretty long time, and you try to get as early as possible first results of your implementations. And how do we do this? You use a so-called virtual prototypes. So that's the thing when chip manufacturers or chip like Intel or Apple, when they try to build a new chip, they try to like simulate it as soon as possible to get first results of how my final architecture will perform. But there's still a big economic risk because you have to imagine currently we're developing our architecture. We do first tests. We develop our prototype, our virtual. But in the end, it's a big investment, and if our architecture is not good enough to face our requirements or the requirements of our customers, you can throw it away. You can try to optimize, but in the end, if the basic architecture is not good, there was a big investment and you cannot really use it anymore. Yeah, thank you for this opportunity, and hopefully there were some interesting aspects for you. And of course, please contact me for any questions or any inquiries. I'm always open to like share information and talk to other companies and partners in this field. And of course, as I already said, we're looking for partners to create future industrial machines. And yeah, we're open to all kinds of interesting use cases. So maybe one of you can share our information, or maybe we talk in afterwards or at any time. Thank you for your attention, and let's do some Q&A.
Yeah, Nikos, thank you very much for the lengthy and detailed explanation. Also to show us a little bit the motivation why to do Edge AI, and also to provide a look under the hood. Actually, speaking of look under the hood, we received 2 questions at least related to FPGAs. So the first one is related to model updates and how you handle this after Edge deployment has happened.
Mm-hmm. Yeah, very interesting. Actually, as I told, of course, we cannot switch to any model, but basically we optimize these models for architecture in the first place when we're not in the field. So we have like a SU, a subset of models. And when we're online on the plant, it's pretty easy to switch models as you know it from other software-based systems. So basically, you switch, you change the parameters, the model, the weights, the instructions. They get loaded into the memory and executed. So it's compared to the common flow when you switch models. It's not that difficult, but in the first place, you have to make sure that the model is running on your architecture, because we don't have a standard GPU based architecture or CPU based. So maybe there are challenges before you actually switch the model to adapt it to your architecture.
Thanks, Nico. And we have another question coming in from Remco. And he asked, what is the best way to optimize for latency throughout while preserving the accuracy of deep learning models on FPGAs?
That's also very interesting, because that's one of the major questions we have to face. We have learned that there is no golden way. Of course, you can optimize for one aspect and not for both of them. So our approach is that we let the customer decide which minimum requirements he has to acquire. And based on these requirements, we can tell him if our architecture reaches these requirements. If we want to optimize for one of these, we have different techniques. I mean, accuracy is basically reached with better data. So we do not only use small data sets, but also smart data. So we try to augmentate the data so they will be used for training and get best results. That's a little bit tricky. That's a tricky thing to do. So there's no really golden way. Throughput is basically done through massive parallel computation. So with our architecture, we have the possibility to like broaden our interfaces, but that's in the same place hurts our latency, of course. That's always the thing with GPU-based architectures. But in the end, every technology has its trade-offs, and I think there's no golden way to like optimize all of the aspects.
Mm-hmm. Thanks a lot, Nico. And we are actually at the end of this session because we have to go into the lunch break, because in a short while we will continue with our afternoon session, which starts off big with a panel discussion featuring our friends from Infineon, AI Storm, but also Silicon Saxony and Silicon Austria Labs. So definitely come back to our afternoon session. We will post the link in the comments. If you're interested in learning more about Danube Dynamics and Nico Theringer, please feel free to reach out to him. He is also on LinkedIn. And thank you for staying with us.
Thank you very much.
Thank you very much.
Thanks
Nico.
a lot, Nico, and looking forward to see you at the next event or one of our next events.
Yeah. Thank you. Bye.
Bye.
Great.
So
yeah, there is not much add from my side. It's just one thing is important to point out. I also wrote this in the comments before. Due to a technical limitation of live streaming on LinkedIn, we always have to separate our events into 2 sessions. So we are now at the end of the morning session. For the afternoon session, we posted the link in the comments, and please make sure that in the AAIC channel, you pick the correct stream, but we will also pin it at the top.
Exactly. And let me just quickly post it. Link to afternoon session. Oh, let's see if that works. Well, it doesn't make a lot of sense to display it here, but head over to our LinkedIn stream or to our LinkedIn page to activate the link to the afternoon session. Good. Then we see each other in 20 minutes.
Exactly. Not much to add. Have fun with the shortest lunch break ever. But see you at 1 o'clock.
See you.